Hello all, welcome to lecture 3 of linear vector space, and in this lecture we will discuss something related to inner product spaces. Any linear vector space in which an inner product is defined are called inner product spaces or unitary spaces. We know how to take the inner product of two vectors in n-dimensional Euclidean space. And we have also defined in our previous lecture how to take inner product of two vectors in a linear vector space. We will just see that once again. If you are given two vectors u and w expanded in terms of base vectors I, then u can be written like this, where small ui's are relevant coefficients for each I value, and small wi's are coefficients of expansion in the expansion of the vector w. So if you are plugging in different values of I, this summation would be like u1 vector 1 plus u2 vector 2 plus etc. un vector n. Similarly for vector w. Now the inner product of u and w is represented by the symbol bra u ket w. So this bracket notation indicates inner product of two vectors. Here we have written the inner product of u with w. I would like to mention at this point that bra vector u is the conjugate of ket u. So while writing the right hand side, it would be ui star wj scalar product ij. We've changed the index of summation to j, but the span is the same from 1 to n for the vector w. Why we have written like this, we will understand as we progress. This vector u, conjugate vector u, this is called prefactor, and this w is called postfactor in the inner product. The inner product obeys certain rules or axioms. We'll go through them one by one. Scalar product of u with w is the conjugate of scalar product of w with u. Scalar product of u with u is greater than or equal to 0, and it is equal to 0 if and only if u is a null vector. Scalar product of u with x plus w is scalar product of u with x plus scalar product of u with w. And we have seen this property in the previous lecture, that inner product of inner product is antilinear in the prefactor and linear with the postfactor. Now, when do we say that two vectors are orthogonal? We say that two vectors are orthogonal if their inner product vanishes. With our ordinary vectors also, we know that when the inner product or dot product of two vectors vanishes, they are orthogonal. Here we are speaking of vectors in general, vectors which are members of linear vector space, and they are said to be orthogonal if their inner product vanishes. Now, we refer to square root of inner product as norm or length of the vector. That also we have taken the same thing from our ordinary vectors, where dot product of the vector with itself would give you the magnitude square of the vector, and square root of dot product would give you the norm or length of the vector. That was for ordinary vectors, and here in the case of vectors which are members of linear vector space, we define the square root of inner product as norm or length of the vector. We say that a vector is normalized or it has unit norm, and we refer to such vectors as unit vector. Any non-zero vector can be normalized by dividing with its length. That also we know. In the case of ordinary vectors in three-dimensional space, we have done all these things. An orthonormal basis is a set of basis vectors which all have unit norm and are pairwise orthogonal. For understanding, you can consider the unit vectors I, j, k, which we take in three-dimensional Euclidean space. We know that each of them have unit magnitude and each are pairwise orthogonal. So an example for orthonormal basis in three-dimensional Euclidean space would be our IJK set of vectors. Similarly, in a general linear vector space, you can have an orthonormal basis, which just means a set of basis vectors which have unit norm and which are pairwise orthogonal. And the advantage of having such an orthonormal basis vector set, this term that is inner product of I with j, that can be written as delta ij, and that will be equal to 1 only if you take inner product of I with I or j with j. If you take inner product of I with j, then it will go to 0 because they are orthogonal. So you can write this inner product of I with j as delta ij, where delta ij is the Kronecker delta, which takes the value 1 only when the indices are the same, and it goes to 0 when the indices are different. So your scalar product of u with w will reduce to ui star wj delta ij, where you have plugged in delta ij instead of inner product of unit vectors I and j. And this is a specific property of the Kronecker delta function, where the Kronecker delta function selects a particular value of the function associated with it. And Kronecker delta function takes a value of 1 only when the indices are the same. That is when I equal to j. So this selects the value of uh, wj when j equal to I. So you get the inner product of u with w as summation ui star wi. Now let's see some examples as to how to evaluate inner product of various vectors. Here vector u and vector w have been expanded in terms of base vectors 1 and 2. And the values given just before the 1s and 2s are the relevant coefficients. You can just imagine that this is u1 and this is u2. And here you have w1 vector 1 plus w2 vector u vector 2. And you are also given 1 and 2 are members of an orthonormal basis, which implies inner product of 1 with 2 would give you 0. And inner product of 1 with 1 and 2 with 2 would give you 1. So let's take inner product of u with u. According to this definition, scalar product of u with u would be given by ui star ui. So just take the corresponding components. When you take ui star, this will be 3 plus 4i. Ui star ui means u1 star u1 plus u2 star u2, which will give you 86. Please evaluate and see. When you take scalar product of w with w, you will take w1 star w1 plus w2 star w2, which will give you 15. Now when you take scalar product of u with w, just take u1 star w1 plus u2 star w2. That is what we have written here. And you needn't take cross components, that is this term with this term, because scalar product of 1 with 2 will give you 0. and you get 35 minus 2y, and you can just see for yourself that this is the conjugate of scalar product of w with u. Now if we go to an example of two matrices, square matrices, 2 by 2 matrices A and B, which are given like this. We had already seen when we saw uh, the case of linear vector space, that is in the previous lecture, that we can define four linearly independent basis vectors in terms of which any 2 by 2 matrix can be expanded in the linear vector space M22. In the case of matrices, the scalar product or inner product of A with B would be written like this: A11 B1 plus A12 B12, A21 B21 plus A22 B22. Now how do we write like this? Just imagine writing A. Just imagine writing A in terms of basis vectors 1, 2, 3 and 4. It would be like this, isn't it? A11 times vector 1. Just imagine what will you get? A11 times vector 1. Vector 1 is this matrix. If you multiply it with A11, you would get a matrix with A11 in this position, isn't it? Now if you do A12 vector 2, you will get a matrix with A12 in this position. A21 vector 3 would give you a square matrix with A21 in this position, and A22 vector 4 would give you a square matrix with A22 in this position. Now if you add all these, you will get the matrix A, isn't it? So you can expand or write any square matrix in this linear vector space in terms of these base vectors. Similarly, you can write B also, matrix B also, and it will be like this. And since 1 and 2 are members of since 1 and 2 are members of orthonormal basis, inner product of 1 and 2 would be 0, and all these are members of orthonormal basis. So any product, any pairwise product would be 0, and inner product of the vector with itself would give you 1. So for a square matrix, the inner product can be defined like this: A11 B11 plus A12 B12 plus A21 B21 plus A22 B22. Please don't confuse it with the ordinary matrix multiplication. Now we see another example. This is a very interesting example. Consider a vector which is expanded in a certain orthonormal basis, and its components are given by the column vector 1 plus I and root 3 plus I, where this I is nothing but our imaginary number root minus 1. Now if you are trying to expand the very same vector in terms of another new orthonormal basis E1 and E2, where the components of E1 and E2 are given by 1 by root 2, 1, 1 and 1 by root 2, 1 minus 1. You can just see for yourself that these are components of a unit vector, because if you take the magnitude of this vector, it will give you 1. Same is with E2. And these two are orthogonal to each other also. Now, if you are trying to expand U in terms of these basis vectors E1 and E2, you will be writing your vector like this, right? Relevant coefficient times E1 plus relevant coefficient times E2. But we need to know how much times E1 plus how much times E2 will give you the same vector U. That is, you need to evaluate U1 and U2. Now, how do we determine U1 and U2 from this relation? All you need to take is to determine U1. You need to isolate U1, isn't it? If we take inner product on both sides with vector E1, with the conjugate vector e1. Then on your left hand side you will have e1 times u, and this term it would be u1 times scalar product of e1 with e1, which is nothing but 1. Now the second term u2 times scalar product of e1 with e2, but your scalar product of e1 with e2 will give you 0 because e1 and e2 are members of orthonormal basis and they are orthogonal to each other. So your u1 can be evaluated as inner product of e1 with u. And how to take the magnitude of a vector or inner product of e1 with u? You will be taking it like this: 1 by root 2 row vector 1 1 and column vector 1 plus I root 3 plus I, and this will give you this value. This we have already seen when we have dealt with orthogonal transformation and unitary transformation. This is how you evaluate the magnitude of a vector when it is given by row vectors or column vectors. Please go through the sections that we have dealt with before when we have seen unitary transformations in the case of matrices. This is how you evaluate. Now, similarly, u2 also you can find out by taking the inner product on both sides with e2. When you take inner product with e2, this term will just be u2, and this term will become 0 because inner product of e2 and e1 is 0, and on your left hand side you will have e2 times u, and when you do that you will get 1 by root 2 times 1 minus root 3. Now to check whether the u1 and u2 that you have got is correct, please evaluate mod u1 square plus mod u2 square, and you will get the magnitude as 6. And the previous components of the vector were given by 1 plus I and root 3 plus I. You take the modulus of 1 plus I square plus root 3 plus I square, and that will also give you 6. This is similar to the case of that we have considered before, rotation of a coordinate system, where the length of the vector is invariant upon rotation, but the components only change. So this is similar to that particular case where you are considering the same vector itself, same vector, but only change in the coordinate system in which you are viewing the vector. Here also you are expressing the same vector in terms of two different bases, and the magnitude of the vector of course has to be same, but the components will definitely vary. So this is all about inner product spaces and how to evaluate inner product and various properties of inner products. Thank you.